Okay, good morning. Let's get through CE amplifier load line analysis, and then well, look at small signal coupling capacitors if we can. Okay, so we stopped right here. Where did we stop? We stop here. Okay, so we drew our load lines by applying KVL on both the input side and the output side. So we have two load lines. Okay, we have two load lines. So let's see what we can do with it. So here's the circuit. In this example, we have VCC is equal to 10 volts. Actually, the circuit, I believe I had some values here. Actually, I don't. All right. All right, so VCC is given as 10 volts. VBB, base biasing, is 1.6 volts. Base resistor, RB, is 40K. RC, collector resistor, is 2 kilo ohms. Okay. And there was no RE in this example. Right? This circuit, only RC and RB. It's the most simplest of biasing circuits and the most simplest of CE amplifiers. Okay, and then your AC input signal, V in of T, is given as 0.4 sine 2000 pi T. Okay, sine 2000 pi T volts. So we are asked to find and sketch V out of T. Okay. So we're going to use load line analysis to see how we can solve for this circuit. All right, first things first. What information do we have from V in of T? Peak voltage is 0.4. Peak to peak voltage will be plus minus 0.4. Frequency F would be 1000 hertz. Omega is equal to 2 pi F. Omega is 2000 pi, so F is 1000 hertz. All right, this is our input signal. .4 volts, 0.4 volts. It's 0.8 volts peak to peak. All right, so V in max is plus 0.4. V in minimum is minus 0.4. All right, on the input side, what do we have? We had our equations right here on the input side, right? IB is VBB plus V in of T or RB. So we will use that equation and we will find the Q point on the input side. So this approach, we want to determine the Q point on the input side using our equations. But this time V in of T is not zero. We have DC voltage being applied, and then we are also applying an AC input on top of that. Okay, so find IB is equal to VBB plus V in of T or RB. So far, so good. Yes. VCC. Question being asked is, are we applying base voltage or DC voltage? VCC. We are. Reviewing the lecture notes for thinking. we'll go back to chapter 4 at the end after this example, because we need to talk a little bit more about the design, which I covered in chapter 4. Okay, so if we just apply DC, ignore the AC for now. DC is what determines your quiescent point, the Q point, right? Quiescent mean lying in a dormant state. In the case of our AC circuits, I mean AC DC circuits here, electronic circuits, it means we apply DC and then the circuit is prepared to accept or lying in wait for the AC input. Okay, so literally Q point stands for quiescent, meaning a dormant state. In our case, it's not dormant, but it's lying in wait to accept AC input. So we apply DC first. V in of t is equal to 0. That gives you your DC biasing point. So we'll have one value for IB for V in equal to 0 volts. Then we find a second value for IB, which would be max value of V in. Then we find a third value for IB, the base current, that's the input, right? Which would be the minimum value of V in. So 3 points. So first find the DC value. In DC value, V in takes on the value of 0 volts. And we can write that as IBQ would be 1.6 plus 0 divided by 40,000. And that gives me 40 microamps. 40 microamps. Right? And then we need to find the max value for IB. So max value for IB would be 1.6 plus 0.4 and divided by 40K. And that should give me 50 microamps, 50. Okay. Again, all we are doing is we're trying to find the Q point. To find the Q point, we need the load lines. For the load line, we saw the equation from last class on Monday. We're just using the same equations. IB min would be 1.6 minus 0.4. And that would be divided by 40K. And that would give me 30 microamps. So on the input side is always base voltage, base current as a function of the base voltage. IB on the y-axis, VB on the x-axis. And because the base emitter junction is forward bias, it looks like a diode curve, right? So I found 3 values of IB. Those 3 values, if you look at the input characteristic, correspond right here. 50, 40, and 30 on the left, plotted on the load line. So those are the 3 points on the load line. Make sense? Hopefully. All right, now to find the voltage, the corresponding voltage, the equation was right here, right? VBE is equal to VBB plus V in of t. So again, if there is no AC input applied, then VBE or the base voltage VB would simply be the applied voltage VBB. So I can say from my equation, VBE is equal to VBB plus V in of t. Okay. And if V in of t is 0, I can find VBQ, the original DC biasing point, VBB plus 0. Therefore, VBQ is equal to VBB, which is just 1.6 volts. So the corresponding point for IB 40 microamps would be VB is equal to 1.6 volts. That is simply the DC voltage and the DC current you would get if V in is 0 or V in is not applied. And you would be able to measure those in the lab. Excuse me. Now, VB max would be 1.6 plus 0.4. So it would be 2 volts. And minimum would be 1.6 minus 0.4, 1.2 volts. So 1.2, 1.6, and 2 volts. And those 3 points correspond to these points right here. 3 points on the y-axis, 3 points on the x-axis, linear line. Draw those lines, and you get 3 intersection points. The intersection point in the middle is your original DC Q point. Okay, that is solely due to the DC biasing voltage, nothing else, because V in of T, AC input, is equal to 0. And then as we increase V in, sinusoidal, square wave, doesn't matter. As V in increases, that Q point moves up and down the load line. Sorry, not the load line. The Q point moves up and down the characteristic. The intersection point changes, right? So you got 3 different points. Let's take a pause, think over that. Let me know if you have any questions. Does this make sense? You have a DC biasing point, so you get so you have DC biasing voltages, you obtain a Q point because of the DC voltage. Then you apply an AC input on top of the DC voltage. So your Q point now shifts up and down the characteristic. Okay. If it's a sine wave and you're looking at a continuous time signal analysis, then you have infinite number of points, right? Infinite number of load lines. But we only want the max and the minimum. So we only plot the max and the minimum load lines. So far, so good. So what do we have now? We have 3 intersection points. Those intersection points give us our Q points for the max and minimum. So the coordinates of these 3 points, actually not even the coordinates, we only need the y-axis coordinate, because the y-axis is the base current that is going into the amplifier. So we only need 3 values for the input of our base current. We don't even need the corresponding voltage. We only need the 3 values for the base current IB. Yes. Yes. So the question being asked is, before we go to the output, we need to solve the load line for the input. The answer is yes, because we don't know what the input is. So it's a very good question. The point of the load line analysis is we want to determine what the output is. To determine the output, we need to know what the input is. And the input is derived from the intersection point. The y-axis coordinates of these 3 intersection points are the inputs to our amplifier. So if we extend these to the left, as you can see here, sorry, not there, right here. It's 1, that's 2, and that's 3. Okay, IBQ, IB max, and IB min. Your base current is just moving up and down between these between those max and minimum values. Okay, so the intersection point, we find IB, it ranges from 35 with 15 microamps to 35 microamps. Okay. Make sense? So now we have the three values for our input current base. Now we take those three values and we take it to the output side, because we need to know which output curve we want to use. All right, so here's the thing though. On the output side, we need a load line. And so on the output side, I'm going to apply KVL, which we did in the previous slide or the previous class. And I'm going to write directly the equation for VCE and IC. So VCE would be equal to VCC, 10 volts. And the coordinates for IC would be VCC over RC. It would be 10 over 2000. This will be 5 milliamps. Okay, 5 milliamps. And those are the 2 points shown here. VCC is 10 volts. IC is 5 milliamps. You join those points and you get that load line. Okay, you get the load line. Ignore the intersection points that are shown right now. Okay, think of it as those 3 dots do not exist. We just have the line for now. We have the load lines from the input side. We took those 3 intersection points, put a pin on those 3 points, hold it in place. We then do the load line for the output side. We have the load line for the output side. It intersects those data points in multiple places, not data from multiple places, but each data set is intersected in one place. We need to know which one we need to use. And for that, we go to the y-axis of the input side. And those are 15, 25, and 35. Input values are 15, 25, and 35. We take that data set and you look at those coordinates. The coordinates of these 3 points is our solution. So let's take a pause, think over that, and then ask your questions, and then we continue from this point. Yes. And let's zoom. Again, if you're just looking at the 2 images, apply KVL on the input and the output side, obtain the load lines for both input and output. There'll be intersection points in 3 places: when Vin is equal to 0, when Vin goes max, and when Vin goes minimum. Take those 3 points on the input side, go over to the output side. Find the corresponding data set for those input values of IB. And those intersection points will give us our solution for IC and VCE. Does that make sense? I'll draw the input and output, and then it'll hopefully make a little bit more sense. Does the process and the steps make sense? Okay. So here's what's actually happening. IB is our input. right? So load line is going to direct our input. So I was to draw my circuit this way. All right. IB is in microamps. Okay. So let's say my IB is like this. This is 0.4 volts and this is 0.4 volts, right? Right now, we are just plotting on IB, but I'm just showing this is V in of T. V in of T goes from 0.4 volts to minus 0.4 volts. And because of V in of T swinging from minus 0.4 to plus 0.4, our IB goes from 15 microamps to 35. Okay. When V in goes to plus 0.4 volts, IB goes to 35 microamps. When V in goes negative, for the negative half cycle, when it goes minus 0.4, IB is 15 microamps. Look at the corresponding IC. As I said, the coordinates of these intersection points give us our solution. So that's 0, and IC swings between what? 1.5 milliamps and 3.5 milliamps. So this would be 1.5. So it would be 3.5. Okay. And obviously the numbers here are, it's a problem, so it's nice round figures. You got input of 35 microamps, you get 3.5 milliamps. Obviously, real life experiments would never work this, with these kind of numbers. More importantly, look at VCE. VCE is our output voltage. So let me scroll down, and just enough to fit V in. Okay. So that's 0. That's straight, approximately. Okay. When IB or V in goes max, when V in goes max, meaning plus 0.4 volts, IB goes to its max value. IC also goes to its max value. What happens to VC at that point? What is the value of VCE? No, when IB is max. When V in goes max, when V in is plus 0.4 volts, top of the positive half cycle, IB goes to 35 microamps. IC goes to its max value, which is again 3.5 milliamps. What is the value of VCE? 3 volts. So it's actually going like this. And when V in goes to its negative, meaning the minimum value, which is minus 0.4 volts, IB goes to its minimum value, which is 25 microamps. IC also goes to its minimum value, which is 2.5 milliamps, and VCE goes to max value, which is 7 volts. Hence, 180 degrees out of phase when compared to V in. All right, let's take a pause while you digest all of that. Let me know if you have any questions. Yes. Yes, I'll talk about that. Designing the amplifier, which is what we need for today's lab. But does everybody understand the graphical analysis? This is how it would work. One other point to note, V in does not have a DC offset, meaning there's no DC component in V in. But because we are applying VCC, the output has both AC and DC. So the midpoint for V in would be 0 volts, but the midpoint for your output voltage is at 5 volts. So there's a 5 volt DC offset in our output. So if we wished to remove that, we'd attach a clamper circuit at the end of our output. We want to bring it down -5. All right, questions? Obviously, these three are not to scale. IB actually looks the biggest, but it's obviously not to scale. Microamps, milliamps, and then volts. Six point 7 voltage. All right, so one final observation would be that the input current what is our input current? Which quantity is our input current? IB. IB ranges from 15 to 35 microamps. Our output current is IC, and IC ranges from 1.5 milliamps to 3.5 milliamps. Input voltage would be the base voltage VB, and if you say that, sorry, should have silenced that. Silence. Silence, yeah. All right, VB or VBE, you look at solely VBE as the input voltage, look at how small the change is. And even this, I'm exaggerating. Probably changes by like less than half a volt, right? It's a 4 bias diode. And so the change is very, very small. Very small change in the input base emitter voltage. But if I just take VB as my input, and VB changes from 1.2 volts to 2 volts. And my output voltage, VCE, goes from 3 volts to 7 volts. Okay, 3 volts to 7 volts. My actual AC input is only minus 0.4 to plus 0.4, so a swing of 0.8 volts. Swing of 0.8 volts at the input produces a change of 4 volts at the output. Okay, so actual V in of T is 0.8 volts, and V out of T would be 4 volts, peak to peak values. Okay, peak to peak. Thus, amplification. The simplest way I always like to describe it is basically saying that whatever DC value you apply to the output side, the BJT or the amplifier takes the AC signal, sorry, it takes the DC voltage and gives it the shape of the AC signal. Okay, it takes the DC voltage and gives it the shape of the AC signal. All right, we have 20 minutes left. Questions? Yes. Oh, so question being asked is, what was it about bringing down by 5 volts? So it was here. So our AC input does not have any DC busing. So I'm right here. V in of t does not have any DC component, but my V out of t is at 5 volts. So if I was to draw or graph this on the same graph, and this would obviously not be to scale. My input would be, if this is my V in of t, this would be 0.4 volts minus 0.4 volts. And my V out would be, let's say, it's at 5 volts. Actually, I should have. All right. So I've made a hash of it, but anyway, that's 0 volts right there. And let's say this is, and again, randomly, not to scale, 5 volts here. This would be something like this. Five volts. It's going from a 3 to 7, right? So let's say this is 3 volts. And this would be 7 volts. So it would go like this. And then 7 volts is here. There. Does that make sense to everyone? This is your V in of t. This is your V out of t. It's obviously not to scale, but the numbers would be on the same graph, meaning your V in of t is at 0 level, no DC offset whatsoever, no DC component. A V out of t has a 5 volt DC plus 5 volt DC component added to it. So if we wished to just have the pure AC signal, then we'd have to bring that waveform down by removing that plus 5 volts DC. As a real life example, have you ever taken like one of those small speaker drivers and connected directly to a battery? If you do that, then all you would hear is like a buzzing sound. That's all you'll get from your speaker. Okay. I did that a lot when I was a kid. So you take a 1.5 volt battery, take one of those small speakers, just connect a DC, connect it to the battery. You'll just get, it's an inductive coil. It's a straight DC line, stores the charge, and then all you get is a buzzing sound. The cone is just buzzing because it's not going back and forth, right? If you want the pure AC signal, but you have a DC component on it, you would hear the AC sound. Let's say you're playing a song, you'll hear the song, but in the background, you'll hear zzz. You got to remove that 5 volt DC. And that's where the negative clamper would play a role. You would add a negative clamper at the end of the output of this amplifier with a minus 5 volts. So it will shift and remove that minus 5 volts, plus 5 volt DC. Okay. All right, let's go back to the design we did in chapter 4. So this was the last slide of chapter 4. Remember, I said this is what you would do in Prelab 8. Okay. In this particular example, my RC was 1 kilo ohm, RE was 470 ohms. Okay. And then in Prelab 8, RC is 4.7K. Everything else is to be determined. Okay. So if you analyze this using the load line technique, we do exactly the same thing. We'd want to find, determine the load lines for the input and the output side. Actually, in this case, we just want the output side. And then we want the input points, meaning where it's swinging. That means I want the current input that's going into the base, my AC input current, right? And so from lab 7, you'll have your characteristics. If you wish to find, if you wish to design a C amplifier, you'd want it somewhere in the middle of the active region. So we'd find a point somewhere here. And as I understand, with the transistor that we are using, it may or may not always be possible. Like some of you might obtain a load line that might be something like this, like way out, right? So what I would suggest is just take that intersection point in the middle and then run a few simulations on PSpice and see how it works out, okay? So in this case, again, on the input side and the output side, I want a starting point. So my starting point is something I obtain from the graph, from the characteristic, okay? So in lab 7, you have your characteristics, you plot the load line. Once you plot the load line, you'll have an intersection point. In that intersection point, find a value of the base current somewhere in the middle. 15 microamps, 20 microamps, 25, 30 microamps. And take that point, and you'd have a value for VCE and IC, okay? So right off the bat, when you assume a value for IB, you get a corresponding value for IC. From IB and IC, you can calculate IE, okay? And then you can calculate VB. Once you calculate VB, you need to calculate the base resistors RB1 and RB2. And for that, you do this. You have IB, you choose IR2 at least 10 times IB. IB is the current going into the base. It forms a voltage divider network. So yeah, I think we did this. This slide is where I showed how it applies both to the input and the output side. So your earlier question about where is the input biasing coming from? It's coming from VCC. VCC applies a bias to both the base as well as the collector, both the input side and the output side. Okay. And the biasing is set by the values of R1 and R2. So the ratio of R1 and R2 forms a voltage divider network. Hence, the name of the circuit is known as a voltage divider bias. It is also known as a 4-resistor biasing circuit because there are 4 resistors in there. So if you hear or read the words voltage divider bias or 4-resistor bias, this is exactly the same circuit that they're referring to. Yes. If you have, yes, the question being asked is when should we assume IC is equal to IE and when should we not? If we have the values for IB and IC, no need to make an assumption. So in this case, we have both IB and IC. So there is no need to make an assumption. If we don't have a value, then we got to start somewhere. Then we make an assumption. So we can assume that IE is equal to IC. Even in this case, we have IC as 4.3, right? 4.3, and IE is just 4.33. So IB is small, right? So yes. IB and IC from the characteristic. We don't have to assume a value. So question being asked is what value should we use for beta? Beta is something you'd obtain from your lab 7 data. We applied IB, find the corresponding IC. IC is beta times IB. Or beta is IC over IB. Not the data sheet. The data sheet, there's a wide variation. Beta values would be something you'd obtain from your lab 7 data. So in your lab 7, We obtain a characteristic plot similar to this, right? At least the students in my lab did. So I'm assuming the other labs also, they obtain the same values or similar characteristics. Did y'all not obtain a plot like this one? Huh? For C amplifier, I know my lab's students did, but those of you aren't in my lab. Lab 7? Have you all not done lab 7 yet? Did you not obtain a plot like this, like C amplifier that was like this? No? Okay. If you didn't, then you probably should. You can use sweep and go may or may not work. I don't know. I haven't tried it yet. But manual data collection, you would obtain something like this. Then you plot the load line on it, find the intersection point. Every value of IB, you would have a corresponding value for IC. So you just, if we take a point for IB like this one right here, we extend it to the left, that gives me the value for IC. IC divided by IB gives me the beta. And so everybody's, you have 2 transistors in your lab kit, same model, same manufacturer, same model. So, but the betas might be, widely different. You could have, what was the range? 35 to 100 according to the spec sheet. You might have a 35, they might have like a 70, or in the same lab kit, you might have 135 and 100. So it'd be wildly different. But that's why you need, every student needs to look at the data they collected so they know the beta value for their BJT. And then you use that BJT as a CE amplifier. Okay. All right. So that's the design. That's the pre-lab. Okay. That's what you would use. Okay. One more thing is about coupling capacitors. What properties do capacitors have? They store charge. As a function of frequency, what properties do they have that we use? Yes. And capacitors have filtering properties based on frequency. So frequency response of the capacitor allows us to use it as an electronic filter or electrical filter. All right. So capacitor block DC because the lower the frequency, higher the impedance. 1/2 pi FC. As the frequency increases, capacitor behaves like a short circuit. As the frequency decreases, capacitor behaves like an open circuit. So for DC signals, it acts as an open circuit or blocks. So blocks DC signals and permits AC signals. Okay. So here we have multiple capacitors. C1, C2, and C3. So C1 is used as a coupling capacitor on the input side. Okay. So let's do it this way. On the input side, C1 is going to block DC signals or behaves like an open circuit for DC signals. So what it ensures or what it does is that any unwanted DC signal that might appear at the input side does not shift our biasing point. That's its purpose. Our biasing point is fixed due to VCC. If you apply a DC voltage at the base other than VCC, then your Q point is going to shift. So if you want a good amplifier, this Q point doesn't shift, then you place a capacitor in front that will permit or couple AC input to the base. Okay, couple AC input to the base. On the output side, C2 has the same purpose as C1. Okay. So the capacitor value is chosen such that it would allow the AC input signal to just pass through according to its frequency. You might not even need a clamper circuit. The capacitor might block the DC by itself. Yes. C1 to go to 0. I mean, the reactance, of course, C1. What do you mean C1? C1, the value for C, like you mean 0 microfarads?
Yeah, when you want it to, then you have a low frequency that's like
0 microfarads. No, but with 0 microfarads, you're not connecting anything. Capacitors are very small anyway. The reactance of C1 goes to infinity, or impedance of C1 goes to infinity, not the value of the capacitor. The reactance and the impedance goes to infinity. All right, and then C3, again, blocks DC from affecting the bias point. And then C3 also bypasses any AC signal to ground. So C1 and C2 are labeled as coupling capacitors, and C3 is known as a bypass capacitor. Okay. Let's see. You can leave the others for the next time. All right. We have about a minute left. Any questions? In our lab 8, we are only using the input capacitor. That's it. Yes. Depends on the frequency of operation. So the capacitor values would depend on the frequency of operation. So you're saying C3, do we want a small value for C3? Small value of the capacitor value? The impedance of C3, okay. It allows the AC signals to go directly to ground. So if there's any AC signal coming there, we do not again want it to affect the biasing point. So it blocks the DC. If there's any other stray DC input comes through, then your biasing point would change because your IE would change. So C3, and again, small or big is relative to your design. Depends on what the application is and depends on what our output, what the purpose of the amplifier is, or the values of RE. Yes.
the like trade-off is using like connecting circuit, like the output be that you can like repurpose the design for like multiple different input signals. Like Like, why not just do the,
If you use a clamper circuit at the output. Depends. If the capacitor does a good job, we don't need to do anything else. But if we get something in the output, then we would apply a clamper circuit. Clamper circuit was just an example. Like, okay, this is where a clamper circuit would be useful. So one of the questions that students always ask is, when and why would we use a clamper circuit? So this is an example where if you have a DC component in your AC signal, which is unwanted, then we add a clamper circuit in there to shift or remove the DC offset. But a capacitor would do the job well enough. Okay, we'll end class here today, and I'll see you all on Friday. For those of you who are in the lab, you take your characteristics, find the biasing points, and then you simulate in LT-Spice. Okay, simulate with the beta values that you obtain in the lab. So once you have that, you should be able to see what your output waveform looks like.